Cool. So welcome everyone to the first BP ICAM webinar for 2025. My name is Sofia Marchesini. I will be the chair for today's webinar. I'm a senior material chemist in applied sciences in BP, and I'm actually a former BP ICAM student, so always nice to be back. And it is my pleasure to introduce today's speaker, Professor Ronnie Pini from Imperial. Ronnie is a professor of multi-phase systems at Imperial College London. He has over 15 years of experience in the study of carbon capture and storage technologies, and he has worked on both carbon capture processes as well as subsurface carbon dioxide storage processes. In his laboratory, advanced experimentation is deployed across a range of scales, including imaging, augmented experimentation to study flow, transport, phase equilibrium, and reactions in porous media. These activities are complemented by mathematical modeling and computation across scales, from pore scale models to process design and optimization. Current applications of interest include carbon dioxide storage in saline aquifer, carbon dioxide storage from flue gas, direct air capture, methane abatement, and hydrogen purification. So before we get started, for the attendees, just a reminder that you have the chat, microphone, and cameras automatically turned off. So please put any questions that you have in the Q&A box that you should be able to access, and we will answer them at the end of the talk. And also a reminder that the webinar will be recorded and uploaded on YouTube. So now I hand over to Ronnie, who will be giving us a talk on multi-scale flow and transport processes in CO₂ storage.
Thank you, Sophia. I hope you can hear me well. Welcome, everyone. Good afternoon. Thank you, Sophia, for the kind introduction, indeed, and the opportunity to present our results on multi-phase flow and transport processes in porous rocks with applications to CO₂ storage. So the idea for today is for me to provide some examples of our work, particularly on how we combine experimental work supported by imaging techniques with numerical work to better understand both flow and transport processes in these systems, with a view of better understanding and quantifying heterogeneities in the systems, which are a key feature of indeed natural system like rocks. So before I start, indeed, this is work that we have carried out for several years, and I would like to take some time to acknowledge contribution by the many students and postdocs in my group who have greatly contributed to this work. You see them listed here in alphabetical order, but also I would like to acknowledge the funding agency who have really supported this work throughout the last few years. So I will not need to spend too much time on this particular slide. We are interested in this talk on geologic carbon dioxide storage. So this is a process that is designed to store CO₂ in the subsurface safely and with the idea of preventing CO₂ to re-enter the atmosphere once stored in these deep subsurface formations. The good news is that the technology is already proven at a large industrial scale, let's say a scale of roughly 1 megaton or more per year since the 90s, particularly with the Sleipner project in Norway. There have been more projects, CO₂ storage projects coming online, and approximately these days we have 50 commercial facilities in operation, which store approximately in a cumulative manner 50 megaton of CO₂ a year. And based on the existing project pipeline and the latest reports on those, we expect the storage capacity to reach approximately 600 megaton of CO₂ a year by 2030. So this is actually a very exciting outlook for carbon dioxide capture and storage technologies. Yet I think it's very important to highlight that this number is still below the critical threshold of 1 gigaton or 1,000 megaton of CO₂ a year, which is what is needed to really enable the energy transition, as mentioned in several reports on the topic. So there is still some way to go to reach that target. So our interest is on the fluid mechanics of CO2 storage, with the idea or with the hope that by improving our understanding of the physical processes that take place in the reservoir once the CO2 is injected, we will increase confidence and hopefully increase deployment as well across the world of this important technology. So many of you might be familiar with this cartoon here, which actually depicts the expected evolution of a CO2 plume once injected into a saline aquifers, as shown here. And essentially, the expected evolution is that the CO2 will accumulate underneath an impermeable rock, and it will start spreading horizontally in the reservoir because of buoyancy forces. And so during this process, actually, there are several mechanisms that will act towards trapping the CO2 in the formation. And these processes actually involve both multi-phase flow or two-phase flow, as well as solute transport within the flowing fluids. So initially, the CO2 will start displacing brine in a two-phase drainage process. Eventually, the brine will re-imbibe into the pore space, trapping the CO2 by capillary forces. But this will follow by eventually the dissolution of CO2 into the brine, because brine has some affinity for CO2. So CO2 will dissolve in the brine, and eventually this CO2-rich brine will dissipate by advective transport and diffusion into the reservoir. And so it's fair to say that because the concomitant action of all these physical processes that take place, predicting the migration of the CO2 plume remains still quite a difficult task, right, to achieve accurate prediction. And that's why, some of our studies might be important. So one key aspect, for instance, that is specific to the CO2 brine system when considering two-phase flow processes is that the low viscosity contrast between the CO2 and the brine makes the displacement dominated by capillary forces. And so the practical implication of that is that the resulting pattern of migration might be very different than the one shown in the cartoon that I just discussed in the previous slide. So I'm showing here results from a numerical studies by a colleague of mine, Sam Prevor, also at Imperial College, who has basically shown quite convincingly that the displacement of the migration of the CO2 plume in a realistic reservoir, heterogeneous reservoir, will be affected substantially by the presence of small-scale heterogeneities, right, which will eventually affect the overall large-scale plume migration. So you see the simulation here at the bottom for the heterogeneous reservoir shows a very different pattern and let's say distance covered relative to a more uniform system. And actually, the heterogeneities that drive these differences are heterogeneities, small-scale heterogeneities at a scale much smaller than the scale that is typically considered in large-scale simulation. These heterogeneities are in the capillary pressure characteristics of the rock, right? And in this case, were accounted for indeed through centimeter, millimeter long heterogeneous features in the reservoir. And so over the years, our contribution has been to develop methods to quantify these heterogeneities by providing, therefore, a practical tool that can be used to develop more reliable reservoir models which can account for these small-scale heterogeneities. So our focus has been indeed at the laboratory scale, specifically on understanding the controls of these heterogeneous features on two-phase flow. So at the core of this experimental effort are so-called core flooding experiments where basically you expose a rock sample to carefully controlled two-phase flow conditions of CO2 and brine. For instance, we work with rock samples of the size shown here on the slide, and a key feature that I will use quite often in this presentation today is that during this experiment we deploy X-ray computed tomography to simultaneously monitor, for instance, the saturation distribution of the fluids within the rock sample at a spatial resolution of millimeter to centimeters, right? So significantly smaller than the size of the sample, right? You see here a picture of one of our scanners in one of our laboratories. So nowadays, using these techniques, imaging techniques for augmenting the information obtained from these experiments is quite common to see. Like many labs have these instruments in this lab, and the key, let's say, measures that can be extracted from the experiments are shown here on the right-hand side. So typically, the two fundamental properties that you can fairly easily obtained from these experiments are the porosity and the porosity distribution in the rock sample. You see here a map of the porosity of a piece of rock. You see in yellow and gray the different levels of porosities and the way they're distributed in the sample. And the second key properties is the saturation of the fluids that is obtained during the core flooding experiments. In this case, the gas brine saturation, right? So you see in red color the saturation of gas, and in blue where more water has remained, right? And these properties can be quantified, as I said, at the resolution of a few millimeters, meaning that you're already at the continuous scale when it comes to modeling. But the key message here is that these two properties are indeed the information that you need to be able to characterize or obtain this information about the capillary pressure characteristics of the system, which are the one that I described before, that are the one that drives this particular behavior of CO2 migration in the rock. And so we developed techniques to indeed be able to measure these capillary pressure characteristics. And we developed a method which is a dynamic method. In essence, the experiment itself involves first saturating the rock sample with water or brine, and followed by the injection of your gas phase. It can be CO2 or nitrogen, depending on the experiment, at a specific flow rate. And the experiment then involves actually waiting to achieve steady state, taking measurements using your X-rays about saturations in the system, and then increasing the flow rate and waiting for a new steady state. And I will show you later how we use this information. So the key aspect so first of all, this method is something that was proposed already in the 90s, and we have extended it to indeed for experiments that use X-ray computed tomography, so that we can extend the reach of the method, let's say, to the entire sample. I will show later. The other key aspect in applying this method is to make sure that the conditions are set so that you are always in local capillary equilibrium. And this is indeed achieved simply by making sure that your viscous pressure drop is much smaller than the capillary pressure drop in your sample, which for a CO2 brine system is quite easily achieved because of the large interfacial tension, but also the low viscosity ratio of the fluids. So under these conditions, you can actually derive a fairly simple model, capillary equilibrium model, that can predict fluid saturation profile in your rock, right? And the starting point is Darcy's equation I'm showing here. You can replace the pressure drop by the capillary pressure drop. This is because of the conditions of the experiment. And because there is a unique relationship between capillary pressure and saturation, you can actually do a little bit of working and recasting this equation, and you can actually obtain a nice differential equation that allows you to predict the saturation as a function of the distance, knowing experimental parameters and your capillary pressure curve. right? And so the way you apply it is that you can obtain information about the capillary pressure curve of your rock independently through, for instance, technique like mercury intrusion porosimetry, right? You can perform measurements on small pieces of the sample of interest. You can obtain a functional form of the capillary pressure curve. In this case, we use the Van Gogh-Newton formulation, and you have all the information to solve this equation. Now, for a uniform sample, like this Berea sandstone we are considering here, you can see that this model actually works quite well. So here, the symbols are the results from our X-ray experiments. So the saturation profile at different flow rates, as I mentioned, is an experiment carried out at different flow rates. And the lines are actually the prediction from the model that I just described. And you can see that the model is actually doing a very good job in capturing the saturation profiles at different flow rates. When you move to more heterogeneous or more realistic samples, you see where actually these issues of this characteristic capillary heterogeneities are very apparent. So you see on the right the same saturation profiles. At this time, you can see how the experiment showed this characteristic, let's say, fluctuation in the saturation that might be the results of heterogeneities in the sample. And the simple model can only capture the general trend, but misses this local variation in the saturation, right? And so our contribution has been to develop a model that can capture these heterogeneities. And the idea of this model is quite simple and is a fairly small modification to the original equation. So in essence, you are dividing your rock sample into a number of volume elements, and the assumption is done that each volume element will have its own capillary pressure curve, which is shifted towards higher or lower values, depending on whether the specific volume element will have a lower or higher capillary entry pressure. So it can be more easily or less easily invaded by the gas, right? So the relationship is quite simple through a scaling factor that indeed scales the local capillary pressure to the representative reference one. And so essentially you simply modify your equations to account for this local scaling factor, and you solve the equation only for the particular volume element, and you solve it recursively across the entire sample, assuming capillary continuity. So we apply this method to 3 rock samples that are characterized by different heterogeneous features and also very different properties when it comes to porosity or permeability. You see here the 3 rocks: Ketton limestone, Edwards Brown, another carbonate, and Indiana limestones. You see they have fairly different porosity values, but also very different permeabilities. So we were really interested to also understand the generality of the method. And here you see the corresponding porosity profile in the samples, right? And we were indeed quite pleased to see that the methods, this conceptual method, actually works very well. So you see here now the saturation profiles obtained during the experiments for the 3 rock samples, and the lines are the prediction by the model, now corrected for these scaling factors that I mentioned before, right? And the bottom plots, you see the distribution of these scaling factors, which is a single set of scaling factor for each sample that will capture the behavior at all flow rates, right? And you can see that the different samples will have different ranges of these scaling factors that are needed to capture these variabilities. Now, you might ask yourself, well, how do I get these scaling factors, right? And so to do that, essentially, we applied a I would say, automatic method, which is depicted in this workflow here. So the method is actually very data rich. So you actually make use of the saturation profiles that are measured at each location by the X-ray CT scanner. We actually know, because of the nature of the experiments, what is the capillary pressure profile in the rock. And so the way to obtain the scaling factor is to essentially map this individual capillary pressure curve to a reference capillary pressure curve. So by using the scaling factor, you should be able to scale all these points that you measure during the experiments around a universal curve, right? So this is the way it is obtained. Now, we also showed that actually you don't necessarily need to know the reference curve a priori, like I shown before, but you can actually use the parameters of the reference capillary pressure curve as your fitting parameters. So you can use this in an automated fashion, where basically you use your saturation profile and let the parameters of the reference capillary pressure curve being a fitting parameter so as to obtain the best fit to your saturation profiles, right? And this is actually quite useful because the method therefore allows you not only to capture the saturation profile, but also to obtain this characteristic capillary pressure curve for the specific sample directly with the fluids of interest, right? So you don't need to go through a classic conversion, for instance, from mercury intrusion to the CO₂ water pair, but you can measure this property directly with the fluid pair of your experiments. And actually, you see the curve here that you obtain in the solid lines, which differ from the mercury intrusion curve. Even though the trends are correctly captured, there are differences that are actually quite important. So the method itself allows you to do that. Another important feature of the method is that it can be easily extended to 3 dimensions. And this is because, indeed, as opposed to the fluid saturation, which is highly sensitive to heterogeneities, the capillary pressure itself is weakly affected by these heterogeneities. This means that if you were to plot the capillary pressure profile in the sample, you would see a very uniform distribution of the capillary pressure at every single location. So this means that you know the capillary pressure and you can simply, therefore, extend the method to obtain a scaling factor for each individual elements in your rock sample. And we have done this, and I'm just showing a result that we obtained. So here now on the top, you see 3 saturation maps in terms of the gas saturation maps at 3 different flow rates for this particular heterogeneous sample. And below, you see indeed the results obtained by applying the capillary equilibrium model. And you can see that there is indeed a very nice agreement between the experiments and the results predicted by the model. So the method works really well also in three dimensions. And this is actually quite a useful result because the main output of all these analyses that now you have available what we call a digital rock model. So essentially we have now a model of our rock samples that describes the important heterogeneous features of the sample, which I described earlier when I was discussing the reservoir simulation results. So you have now you have now a tool that you can use to indeed quantify these heterogeneities, which, for instance, this information can be used to identify different type of rock or features in your sample, as we've done as an example in this slide here, where we identified regions of the sample within specific range of this capillary scaling factor, which might be useful when it comes to upscaling exercise where you want to simplify, let's say, the description of heterogeneity in your system. Now, going back to the cartoon with which I've started, so we discuss now let's say the multi-phase flow aspects of CO₂ migrating into the reservoir, but indeed an important aspect and another important physical process that takes place is that CO₂ dissolves in the brine, right? This is a key mechanism for the long-term storage of the injected CO₂. And the question is also now on how these heterogeneities potentially affect the rate of CO₂ dissolving in the brine and eventually also the rate of the CO₂-rich brine dissipating into the reservoir, which eventually is the final mechanism that will enable you to store CO₂ into your reservoir. So a very interesting process that takes place when CO₂ dissolves into brine is that it creates a solution that is denser than the brine, the fresh brine, by an amount of about 10 kilogram per cubic meter, right? And this might seem insignificant, but this actually change in density is sufficient to create an instability, because now you will have a denser solution on top of a lighter solution, create an instability which will start this characteristic convective currents of CO₂-rich brine moving downwards into the reservoir. So this is obviously good news. We like for the CO₂ to go downwards as opposed to go upwards. But the important aspect is also this convection will bring more fresh brine in contact with the main CO₂ plume, meaning that it can greatly enhance the dissolution, right? Because you keep feeding your system with fresh brine. So there have been many studies showing, providing evidence, particularly numerical study of this phenomenon. But we found that until recently, direct experimental evidence that this process actually takes place in rocks, particularly with relevance to the CO₂ brine system, was still lacking. So we decided to undertake an experimental campaign to study this more in detail, because otherwise we are left with large uncertainties on the effective rate of CO₂ dissolution that we might achieve in rocks, particularly in the presence of heterogeneous systems. So we identified an experimental analog to perform these experiments, particularly an analog solute-solvent pair instead of using directly CO₂ and brine, which, however, has the same characteristic as CO₂ and brine when it comes to the change in density with the amount of CO₂ dissolved in the system. Particularly for CO₂ brine, this relationship is fairly linear, and so we identified this salt-water pair that actually has a similar profile, right? And we then used our X-ray imaging techniques to actually monitor this particular process, convective process, into the rock sample over time. And so, first of all, the important observation is that indeed, also in rocks, this process takes place, and actually takes place, indeed, this process enhances the rate of dissolution into the pore volume. So here you see in this graph the total amount of solute dissolved into the water as a function of time. So for diffusive transfer, we expect this rate to follow an evolution over time with the square root of time, right, because of diffusion. And we observed that in all porous media, we had actually a linear dependency with time. So this is a great enhancement relative to diffusion alone. Interestingly, for uniform system, indeed, we had a linear relationship. So this coefficient alpha was roughly 1. We observed something similar for rocks that we consider to be fairly uniform, but actually the coefficient would be significantly reduced when you start working with more heterogeneous systems. So we already have an indication that heterogeneity plays also an important role in controlling the rate of mixing and dissolution of solutes within the brine. And actually the imagery that we obtain from the X-ray computed tomography images confirm that, right? And the interesting observation is that actually the presence of heterogeneities in the rocks disrupt actually the structure of these characteristic columnar plumes that we have seen in the videos that I showed you before. So on the left-hand side, you see results from Bentheimer sandstone, which is a fairly uniform system for which we can still see these plumes, columnar plumes that move downwards into the rock. And here you see the X-ray image of the rock. But as we move to rocks that have more heterogeneities, we see that these patterns is more chaotic and disrupted until we reach this sort of behavior in a very heterogeneous system where you no longer see this sort of long plumes, but a rather diffusive process, right? And we have seen before that actually these are an influence on the rate of dissolution. So we decided, therefore, to study with more detail what are the controls on solute transport. And specifically the role of heterogeneities, right? And this will be the final part of my of my talk. So the way you characterize soil transport in this system typically is by performing tracer tests. So you have your sample completely saturated with water, and you inject a tracer of a substance that you want to monitor, typically a pulse, and you monitor the effluent profile in terms of concentration of the tracer. And actually, the shape of this curve contains all the information of the different mechanisms that take place within the sample in terms of effect that might come from heterogeneities and so on, right? And typically, indeed, you interpret this breakthrough curve using a suitable transport model. Now, the key challenge in interpreting this data is that different mechanisms can lead to macroscopic observation on the breakthrough curve that are actually equivalent. So, for instance, it has been shown that diffusion into immobile porous zones have the same effect as heterogeneities in the permeability of the rock sample. So decoupling this effect is very difficult if you just rely on the breakthrough curve. So we performed several experiments, and we observed that indeed for very uniform samples, these can be random bitback or the bend timer sandstone that I showed you before. If you do experiments at different flow rates, you see that this breakthrough curve actually collapses all into a universal curve. These are typical signs of a simple advection dispersion process that controls your transport in the sample, that is typically described by an equation of this form. And this is expected because indeed, if you go through an exercise of making this equation non-dimensional, you will see that actually the obtained solution will be independent of the flow rate. And that's what we see here. Here you see several experiments in both cases at different flow rates across a regime of Berkeley numbers, and all the data collapse into the same curve. So that's something known and quite something that you can easily predict. However, when you move to samples that are more heterogeneous, and we go back to our carbonate samples I was discussing before, we see that the curves no longer collapse into a universal curve. And you see clearly some effects arising from flow rate dependency. So curves at different flow rate are actually showing a different shape, in addition of the curve being much broader and asymmetric. So the question now is, therefore, if I cannot use this sort of model, the simple model that doesn't have any dependency on the flow rate, which model can I use to interpret these experiments, right? And typically, the model that is used is a so-called multiple rate mass transfer model. This is a model that basically is mathematically an extension of the model I showed you before by adding one term that includes this flow rate dependency that basically describes the interactions between regions that are fast flowing, let's say, in your system, with regions that are less flowing, right? This can be, for instance, due to heterogeneities, right? And typically the fraction of these regions, the volume fraction of the region is a parameter that is typically fitted from the breakthrough curves. And so we applied this model, this more advanced model, to our data set with the carbonate samples that I showed you before. And actually, you can see that it works very well. So these are all our breakthrough curves measured at different flow rates for both samples. And the lines are the prediction of the model, which is quite shows a quite very good agreement with the experimental data. But the problem is when it comes to interpretation, right? And one should always ask themselves whether the parameters that you obtain from this fitting exercise have a physical meaning. So in the case of Keton limestones, for instance, the model was predicting that the fraction of this immobile pore space in the rock was roughly 36%. And actually, this was in very good agreement with independent measurements that we obtained by mercury intrusion porosimetry. You see here on the right, mercury intrusion porosity curves in terms of pore size distribution. The blue curve is Keton, and we see indeed that there is a significant fraction, about the same, 35%, of pores below 1 micron. So these are pores where we do expect only diffusion to take place as opposed to flow. The same model, though, for the other rock was predicting also a fairly large fraction of this immobile pore space in this other carbonate rock, but we don't see these pores in independent measurements. Actually, we see a much smaller fraction. So this might indicate that the model was providing a very good fit to your data, but mostly because of an additional parameters, but was not presenting, let's say, the correct physical interpretation of the transport process. And that's where we resorted again to imaging techniques to better understand what was going on. In this case, we used a different tomographic technique called positron emission tomography, which allows you to monitor indeed the displacement of a radio tracer in space and in time, right? And you see here the 3 rock samples that I just discussed, their porosity distribution on the top, and the bottom you see the sort of information you obtain from these tomographic experiments, where you see clearly this pulse of tracer moving through the rock sample, right? And if I just stop the video, for the uniform sandstone, you see indeed that the pulse remains quite intact and moves as a piston almost through the rock sample. But with the more heterogeneous samples, you actually see a significant distortion of the tracer, potentially due to these heterogeneities in the sample, but also some other interesting effects, like in the case of Keton, where you see this cloud behind, which might indicate the presence of this immobile pore space where exchange is only happening by diffusion. Right, and so we decided therefore to look at this data in more detail. And so what you can do, so one very useful information that you can do, because when you have this sort of data set, is that you can actually extract much more information about the transport process in the rock sample. So as opposed to just analyzing a breakthrough curve, we can actually extract, in this case, the spatial moments of the solute concentration field as a function of time, right? And here I'm just showing the behavior of the first 4 spatial moments that are directly extracted from the images obtained in the experiment. And this actually, the behavior of these moments contains a lot of information about the key transport processes in the sample, right? And in the case of a uniform rock like the Bentheimer sandstone, we can see actually that we are able to predict, this is the results indicated by the solid lines, quite with great accuracy, the behavior observed experimentally. So this gives us confidence that the measurement techniques is precise, and we do observe the expected behavior. To obtain the same information for the more heterogeneous samples, we had to resort to a more complex numerical model, in this case a 3-dimensional model, so that we can account for heterogeneities in the sample. In particular, we used ModFlow, which is an open source code developed by the US Geological Survey, right? Where you basically start from your porosity map, which you obtain from X-ray tomography. You can predict the field of the hydraulic conductivity using a specific relationship. And using that, the model solves the flow equations, conservation of mass, basically, to obtain a velocity field, which reflects the heterogeneity of your rock sample. And then on top of this field, you can solve your transport equations, for instance, the advection dispersion equation that I was mentioning before, right? And then you can compare these results to your experiments, and equally you can extract the moments or the spatial moment of the concentration distribution and compare them to your model. And this exercise has been very, very useful because indeed for the specific, for the rock for which we were not able to correctly interpret the data, we made some interesting observations. So here on the left-hand side, you see again the tracer breakthrough curve. The data are the symbols. You see in red the results of the one-dimensional multi-rate mass transfer model I discussed before. And in green, you see the result obtained by using this 3-dimensional model, but this time using the simple advection dispersion equation with the addition of the heterogeneities that are now accounted for from the velocity field. So you can see that the breakthrough curve don't change much. So you see what I mentioned before, that the breakthrough curve alone doesn't allow you to distinguish which model might work best. But when we started looking at the moments, we did see where actually the 3-dimensional model did predict the correct behavior observed experimentally. We are not yet fitting the data precisely, but we do see that the trends are correctly captured, as opposed to the multi-rate mass transfer model, which actually shows potentially also the opposite trends as opposed to the one that you should observe. So this is again to say that knowledge of heterogeneity is very important also for transport processes, and these imaging tools allows you to do that, to incorporate these heterogeneities and to verify that you indeed are using the correct model formulation for interpreting your data. Right, and obviously you can compare the predicted solute concentration profile in the sample from the model to the one observed in the experiments, and visually you can see that the two are now looking very, very similar. Great. So bringing now everything together to conclude, I showed basically two different approaches supported by imaging techniques, two different but complementary approaches supported by imaging techniques to study multi-phase flow processes through indeed generation of saturation maps and producing this and providing an information to quantify the heterogeneity in the samples, as well as techniques, imaging techniques that allows you to monitor transport processes in your rock sample, right? The two are obviously complementary, but we think we have now the tools where we can actually develop a unified workflow where this all this wealth of information is combined and used to basically quantify and account for heterogeneities in measurement interpretation, which is key to provide reliable estimates of parameters that then can be used, for instance, in upscaling exercises, right? And this is something we are currently developing, where now we try to combine all this information to provide a more consistent interpretation of these data sets in the same, let's say, rock samples. So that's something for us for the future, which we hope to complete soon. So coming to some concluding remarks. So I think a key message that I gave at the beginning is that subsurface CO₂ storage entails really concurrent action of many different physical processes across a wide range of scales, from flow to transport processes. Laboratory experiments, particularly those supported by three-dimensional imaging techniques, offer really an opportunity to gain more insight into the underlying flow and transport processes. In our particular case, we deployed a multimodal approach where we use different imaging techniques, X-ray computed tomography and positron emission tomography, to study both flow and transport processes. And we think that this combination provides a unique opportunity to create a unified framework to interpret these measurements. Particularly, we are using this tool to provide three-dimensional mapping of important properties of flow and transport that can be used as key input parameters to numerical models and to develop more accurate reservoir models. And obviously, these are tools that can be used to tackle more complex problems. I mentioned still an open problem for us, which is the one involving natural convection, so these characteristic fingers, which we are now able to tackle, but also other problems where flow or transport is coupled with chemical reactions, which we have not considered yet. And with this, I would like to thank you for your attention, and I'm very happy to take questions. Thank you.
Thank you very much, Ronnie.